Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. Don't you find celestial geometry incredibly fascinating? Yes, me too. Comments from 2 of my viewers inspired me to make a video on the topic of Moon's 3 motions. On my online video tutorial channel, knowledge-seeking enthusiasts with further interest will find a wide choice of variety of immensely elaborate video lesson series. Prior to watching this video, viewers are advised to watch my video lessons on lunar nodes, lunar standstill, as well as Earth's 3rd motion. Please note that illustrations are not to scale, and certain illustrations have been exaggerated for the purpose of comprehensible clarification. According to Newton's laws of motion, all periodic orbits are ellipses. So, as we can see, this is one thought-provoking aspect of lunar revolution. Moon's tortoise pace. At a rate of 13 degrees per day, denoted by the sector of 2 radii and an arc, it takes roughly 7 days for the Moon to traverse through a quadrant on its orbit around the Earth. That is to say, it will reach the opposite side of the orbit, a semicircle arc, revolving 180 degrees, in about 2 weeks' time. And what does that mean? If you look at the red weeks of the month on the calendar, indicating the Moon spends 2 weeks around one side, traveling half orbit. It spends next 2 weeks around the other side, completing 360 degrees. So the question one would ask, if that's the case, then why do we see the Moon rises, travels across the sky, and sets almost every day? Even though the Moon is very slow on its orbit around the Earth and revolves only 13 degrees per day, we have to remember that the Earth is rotating faster on its axis, one full 360 degrees within just 24 hours. Which means Moon's passage across the sky every day is caused by the Earth's rotation. While the Moon is traveling at a tortoise pace, hanging around on one side for 2 weeks, the Earth is catching up with it anyway. The next subtopic in Lunar Revolution 1 would like to study is Moon's sidereal and synodic periods. In this subtopic of Moon's axial rotation, we are going to explore another intriguing aspect of Moon's orbital dynamics, synchronous rotation, in the matter of orientation of lunar hemisphere. So, oddly enough, as strange as it may seem, we can see that Moon's axial rotation and orbital revolution periods happen to be equal. Okay. Now that we have got a succinct overview of lunar revolution and lunar axial rotation, hereafter we are going to delve into the third motion of the Moon, lunar precessions, pertaining to its orbital plane and rotational axis. Prior to the actual geometrical illustrations, let's briefly saunter through a couple of key definitions and clarify the fundamental concept. The rotational axis of the Moon also undergoes precession. Moon's axial precession refers to the perpetual change in the tilt of Moon's spin axis. Once every 18.6 years, lunar North Pole traces a small circle around a point in the constellation Draco, while lunar South Pole traces a small circle around a point in the constellation Dorado. Well, on the other hand, the orbit of the Moon undergoes two types of precessional motion, apsidal and nodal. Apsidal precession refers to the gradual shift in the orientation of the lunar orbit. The major axis of Moon's orbit rotates in the same direction as the orbiting Moon itself. The line of the major axis of Moon's elliptical orbit, connecting perigee and apogee, precesses anticlockwise with a period of about 8.85 years. Apsidal precession is a key factor in understanding orbital dynamics, as Newtonian mechanics alone doesn't suffice. Now, let's also perceive nodal precession. Constant movement of the intersection between lunar orbital plane and the ecliptic, as the lunar orbital plane slowly turns, carrying the two crossing points' lunar nodes on it. Now, let's imagine a combination of these two. Moon's apsidal precession, along with its nodal precession. How to visualize the net effect? Precession of the line of lunar orbit's major axis is in fact a precession of the shape of the ellipse. It's anticlockwise, that is to say, eastward. While its nodal precession is essentially a precession of the line connecting the lunar nodes, the nodal line. It's however clockwise, namely, westward. In this illustration, please observe the shift of the apsidal line in fuchsia color, and the nodal line in red color, relative to their previous orientations in the first settings. These three remarkable forms of lunar precession, occurring together at different periodicities, ultimately cause the widely varying eclipse calendar. In the context of lunar precessions, a profound insight into the geometry of lunar tilts and inclinations is utterly crucial. Here you see a comparative illustration of the axial tilts of the Earth and the Moon. Earth's axis is indicated by sky blue dashed line. The direction of the Earth's equatorial plane is indicated by sky blue dotted line. The direction of the Earth's ecliptic plane is indicated by bright yellow dotted line. As we already know, Earth's equatorial plane and ecliptic plane are at an angle of 23.5 degrees with each other. The direction of the Moon's orbital plane is indicated by white dotted line, which is at roughly 5.2 degree angle with respect to Earth's ecliptic plane. In this illustration here, the Earth's orbit is shown in bluish ash-gray color on pale sand color ecliptic plane, whereas Moon's orbit is shown in fuchsia color on lilac color orbital plane. Half of the Moon's orbit, denoted by dotted curve, happens to be below the Earth's ecliptic plane. The two planes intersect at the bright red solid line. Here you see simplified graphical representations of combined Earth-Moon tilts and inclinations. These illustrations and animations demonstrate nodal shift, transition in the orientation of the nodal line, denoted by red color. Now, imagine perpetual nodal shift like this. Combination of a revolving nodal line and a constant tilt. Why such combination matters? It's significant because this is what eclipse seasons originate from. Orbital plane orientation varies, but axial tilt remains constant. Can you tell me how that is possible?
Ready lecture notes and study materials are available on request. Please use the comment section below for further academic discussions. Viewers' suggestions and ideas of new video lesson topics are gratefully appreciated. Stay tuned for more uploads. Please remember to like, subscribe, share.